Good morning, friends. Welcome to this video lesson. This video lesson is on the topic called simple stresses and strains. We have made one video lesson on this topic only earlier. This video lesson is continuation to the earlier one. In the previous video lesson, we have discussed about what is a stress, what is a strain, what are the various stresses like tensile stress, compressive stress, and shear stress, and various strains. So volumetric strain, tensile strain, compressive strain, or shear strain, all these things we have seen. And also we have gone through the hoop stress, that is how to define Young's modulus, and all these things we have seen. And also we have gone through various mechanical properties such as strength, ductility, malleability, hardness, fatigue, resilience, toughness, brittleness, and all these things we have seen. So in this class, we will be continuing from there. So this video is especially useful for diploma students of Telangana state. So let me continue from there. That is, we are in this video lesson, we will be discussing about the rest of the parts in simple stresses and strains, such as what are the various elastic constants that we have, and also we will be going through uh, stress and strain diagram for ductile and brittle material, and also what do you mean by factor of safety and what is its significance, and longitudinal strain or linear strain or lateral strain, Poisson's ratio, and all these things we will be going through it. So I'm sharing one PowerPoint presentation, and accordingly we will go. So here is my PowerPoint presentation, continuation to the earlier topic. So simple stress strain curve for ductile material. So how it will be? Ductile materials means the materials which will have the property called ductility. What is a ductility? Ductility is nothing but the ability of a material to deform under tensile loads. This is what best example for the ductile material is mild steel. So we will see how the stress strain diagram will be. That means this is the stress strain diagram for the ductile material. Stress is on the y-axis and strain is on x-axis. So how this elongation process takes place, that is not. So otherwise load versus elongation, also we can say this one, or stress versus strain diagram, we can say that. And we will go through what are the various salient points that are given here. If you see here, this is when there is no stress, and of course there won't be any strain. So it starts from the point O. As long as the stress increases, so the strain will also increases, or as long as the load is applied, it will deform, so elongation takes place. So this is how. And we will go through various points. Point A, B, C, D, E, and F. What are these? We will go through it. First one is point A. What do you mean by point A? It is a proportionality limit. So the curve starts from the origin O and up to point A, it is straight line. That is directly proportional. Stress is directly proportional to strain up to the limit of proportionality. So which represents the stress is directly proportional to strain. So the point A is known as proportionality limit. So a point is called proportionality limit. Up to this point, the stress is directly proportional to strain, and the line will be a straight line. So this is what we have. And the next point is point B. This point B is called an elastic limit. What do you mean by elastic limit or elasticity? So when we apply a load on a body, it will deform or it will elongate. When we remove that load, it will come back to its original position. And if any material exhibits such property or such such property is called elastic material, and that property is called elasticity. So these ductile materials will behave like elastic material up to certain load. Beyond that certain load, uh, it will not be an elastic material anymore. So it will become a plastic material. That means when load is removed, it will not come back to its original position. So the point B here indicates the elastic limits. So up to point B, the material remains elastic. That is, on removal of the load, no permanent set is formed. Yes. So if we remove up to this load, if we remove, it will come back to its original position. So that's why. But here one difference is there. There is a difference between O to A is straight line, but from A to B, it's not straight line. A little curve will be there. If you see here also, a little curve will be there. But it almost looks like a straight line, but it's not so. So the point B here is elastic limit. So AB is not straight line. The point B is called elastic limit. And next point is called upper yield point and lower yield points. Here you see here C and D. If you know that beyond B, if the load is applied beyond B, then it will no more, the material cannot be called as elastic material. So it loses its elasticity. So it will become a plastic material. So the deformation, when we remove the load also, it will not come back. That means we can say it's a permanent deformation. So beyond B, if we apply load or the stress is more, then we can find two more points, that is called C and D. So C is called upper yield point and D is called lower yield point. So beyond point B, the material goes to a plastic stage until that upper yield point E is reached. So at this point, cross section of the image of the material start decreasing and the stress decreases to a lower level value to a point D is called lower yielding point. So beyond A, B, that means up to B it is elastic deformation, beyond B plastic deformation starts. So it reaches to the point C, and from there we can see the area of the cross-sectional area of the material starts reducing because of the elongation process. So because the area gets reduces and its value will get the stress value will be reduced. So the point C indicates upper yield point and the point D indicates lower yield point. And next point is called E, point E. So E is called ultimate strength. Ultimate strength. Beyond D, beyond point D, the specimen elongates by a considerable amount and the strength of the material increases, thereby requiring more stress for deformation. So until point E is reached. So this is what happens. So it requires a considerable amount of the strength for its for the material to be increased. Therefore, up to point E, the strength will increase. That means the stress will be more. So point E is called ultimate point, and the corresponding stress is called ultimate strength, ultimate stress or ultimate strength. So this is the maximum strength that a material can have, or the maximum stress that a material can have will be the point E. Next point is called a fracture or breaking point. So at point E, necking of the material begins. That means because elongation, the area gets reduced, and the reduction of area will become localized uniformly initially from D, from beyond B or beyond C. The cross-sectional area uniformly gets reduced. But after E, what happens at a particular where the in the entire span, it will identify the weak point, and there the localized area will be reduced at a particular point, gradually increases. So it will be concentrated only on that particular area. That's why it is called necking. So at point E, necking of the material begins and the cross-sectional area decreases at a rapid rate until the specimen breaks at a point F. So from D to E, a gradual decrease in the area, but beyond E at a particular point on the specimen, not the entire specimen, but only at a particular place, the necking starts, and the decrease will be at a rapid rate, and at a particular point it will break. The stress at which the failure occurs, that is it breaks, it is called breaking point or breaking stress or fracture stress. So this is what, these are the important and salient points in a stress strain curve diagram for a ductile material. So this is for ductile material. So we have a point A, B, C, D, E, F. A is a proportionality limit, B is elastic limit, C and D are yield point, C is upper yield and D is a lower yield point. E is the ultimate point, that is the maximum stress that it can have, and point F is nothing but breaking point. And beyond E, the stress reduces and necking starts, and the decrease in the area in a particular point at particular place on the entire span rapidly increases and finally breaks. So these are the important and salient points in a stress strain diagram. Now, stress strain curve for brittle material, we will see how the brittle material will be. Now, it looks like this. Stress, it's a simple. What is a brittle material? So brittle materials will not elongate. That means when we apply load on that with little deformation, which is not to be considered, or without any deformation, it will break. So if there is no elongation on a tensile load, or if we not have any compression on or with little compression on compressive force, then the material is called a brittle material. So brittle materials are those which break suddenly under stress at a point just beyond elastic limit. This is what we have. So stress strain, after stress and strain, elongation starts, a little elongation, which is when we compare with the ductile material, brittle material performs negligible deformation or no deformation in some cases. So they have little or no yielding before failure, and their percentage of elongation is very low. So after the elastic limit, it will try to protect, but beyond that, it won't show any yielding or a little yielding before the failure occurs. So this is what. So stress when applied, and after the elastic point, it breaks. So if the percentage of elongation is equal to or less than 5%, that means then the material is considered to be a brittle material. The 5% is a very small amount. So if any material shows less than 5% of elongation, we can consider that material as a brittle material. Examples of brittle materials are glass, concrete, cast iron, and plasters, and all these things are the examples of brittle material. So this is a simple stress strain diagram or stress strain curve for brittle material. Earlier one is for ductile material, and this is for brittle material. Now we will go through Hooke's law. What is Hooke's law? When a body is externally loaded, then the stress induced in the body is directly proportional to the strain up to proportional limit. So we have seen in the stress strain diagram, initially from O to A, the curve indicates that it's a straight line. That means stress is directly proportional to strain up to certain limit. That limit is called proportionality limit. So Hooke's law says that uh, uh, when a body is externally loaded, then the stress induced in the body is directly proportional to the strain up to the proportionality limit. So mathematically, if you want to give stress is directly proportional to strain, and stress is equal to, when we have taken out that proportionality limit, so it is called some constant, and that constant we will be indicating with E. Therefore, constant E is equal to stress by strain, that is sigma by E. And this E is called Young's modulus or modulus of elasticity. So here the constant of proportionality E is called modulus of elasticity or Young's modulus. So it's a definition: stress by strain, the ratio of stress to its strain is called modulus of elasticity. But when it is subjected to a tensile loads, only this proportionality is called modulus of elasticity or Young's modulus. So SI units for modulus, Young's modulus is nothing but because strain we won't have any units. Therefore, whatever the units of stress, that only the units of the Young's modulus. So for SI units for Young's modulus is Newton per meter square. Now we will go through various elastic constants. So we have, depending on the nature of stress and strain, there are three elastic constants. What are those three elastic constants? One is the Young's modulus or modulus of elasticity. Second one is called modulus of rigidity. Third one is called bulk modulus. Now we will go through in detail what are these. Just now we have seen what is modulus of elasticity or Young's modulus. The ratio of tensile or compressive stress to the corresponding strain is called modulus of elasticity. So modulus of elasticity means the stresses should be either compressive or tensile, and the strain is corresponding. If the tensile stress is there, tensile strain will be there. If the compressive stress is there induced, then the corresponding strain will be compressive strain. Therefore, it is denoted with E. Modulus of rigidity is nothing but tensile stress by tensile strain or compressive stress by compressive strain. Therefore, sigma by E is modulus of elasticity. So the ratio of tensile or compressive stress to the corresponding strain is called modulus of elasticity. The second one is modulus of rigidity. Here, the nature of stress and strains are shear ones. That is, the ratio of shear stress to the resulting shear strain is called modulus of rigidity. We have seen what is a shear stress and shear strain in the last video lesson we have gone through. So the ratio of shear stress to the corresponding shear strain is called modulus of rigidity, and it is denoted with the symbols called C, G, or N. In some textbooks it is written as C, in some other textbooks it is written as G or N, depending on the textbook writers. So these three are used by various authors. So it is denoted by C, G, or N. But for our convenience, we will be using in the form of C only. So from now onwards, a C means its modulus of rigidity. So modulus of rigidity C is nothing but shear stress by shear strain, that is tau by pi. So this is what is a bulk modulus? When a body is subjected to three mutually perpendicular direct stresses of equal magnitude, then the ratio of direct stress to resulting volumetric strain is called bulk modulus. For example, we will go through a figure. So this is the body and it is subjected to three mutually perpendicular stresses. See here, load in this direction. All these are compressive loads. So, and mutually perpendicular and equal magnitude. So if you see the load applied here is equal, therefore the stress will be equal. So because the cross-sectional area is equal in all directions. So this is what we have. The mutually, when it is subjected to three mutually perpendicular direct stresses of equal magnitude, then the ratio of direct stress to the resulting volumetric strain is called bulk modulus. Do you know when the loads are applied here like this, it will be subjected to a change in volume. So volumetric strain is change in volume by original volume. So the stress by load, stress by its strain, volumetric strain. Direct stress by volumetric strain is called bulk modulus. Therefore, it is denoted with letter K. So bulk modulus is nothing but direct stress by volumetric strain, and direct stress is indicated with sigma and volumetric strain is EV. So these are the three elastic constants. So the three elastic constants are modulus of elasticity, modulus of rigidity, and bulk modulus. Modulus of elasticity is something deals with tensile stress or compressive stress to the corresponding strain. Therefore, tensile or compressive stress by tensile or corresponding compressive strain is called modulus of elasticity or Young's modulus. Shear stress by shear strain is called modulus of rigidity, and direct stress to the volumetric strain, that is the ratio of direct stress to the volumetric strain, is called bulk modulus. These are the various elastic constants in this chapter. So now we'll try to understand the concept of factor of safety. What do you mean by factor of safety? So when we design, that means in practice, engineering components or parts are designed with a margin of safety. I would like to tell one example here. That means we can see that generally a bike or a bus or a car, if we see, it is designed for a limited capacity. If we take, for example, a bus is for a 40 members or a 50 or 60 members at the most, or a bike is for 2 members, or a car is for 4 or 5 members. But even more number of passengers are there in either car or bus. Sometimes we see 5 or 6 members will be sitting on a bike, or as many as 10 members will be sitting in a car. But even it is designed for a lesser number, that is for 4 or 5, still that car works. The reason here is the components or the machines are designed with a margin of safety. Even if you see, sometimes we see when a rush is there, a bus, as many as 100 members will be boarding on a bus. So, but even then, that bus will move without any failure. The reason here is the machines or instruments are designed with a margin of safety. Because of the safety, even beyond that limit also it will carry. Of course, it is not advisable to go beyond the same designed ones. So this is what a margin of safety. Let us try to understand what do you mean by factor of safety. The stress allowed in any component under working condition must be less than the stress which causes fracture or a failure of the component. For example, I'm designing a shaft. The shaft can bear up to for example, a shaft can bear 200 kilonewton per meter square, or 200 Newton per millimeter square, for example, if it can bear. So I cannot put a load or a stress beyond that. That means if I apply any load which creates a stress more than 200 Newton per millimeter square, then obviously that material will be it will fail. So failure occur and break it will break. So this is what. So I should apply less than 200 Newton per millimeter square, and even I will go a limit. That means I will apply only 150 Newton per millimeter square stress. So if I keep it as a design factor as only 150, that means the maximum stress that it can bear is 200, but I am allowing working stress should not be more than 150. Therefore, that material will not fail under any circumstances, because up to 150, that means I have a margin of safety of 50 Newton per millimeter square. Therefore, this is because the safety and working of the components are very important. So the stress allowed in any component under working condition must be less than the stress which causes a fracture or failure of the component. Therefore, a safe working stress is therefore chosen according to the working condition and the nature of the load. This is what we have. Therefore, the ratio of ultimate stress to the design stress or a workable stress is called allowable working stress is called factor of safety. Therefore, the mathematically factor of safety is ultimate stress by design stress or allowable working stress. For example, in our case, I said ultimate stress is 200 Newton per millimeter square, and design stress I am giving is 150 only. Therefore, 200 by 150, it is 4 by 3. So the factor of safety should always be more than 1. If it is less than 1, that means we are allowing design stress more than ultimate stress, which leads to failure. Therefore, the ratio factor of safety is nothing but ultimate stress by design stress or allowable working stress. For a ductile material, the yield point stress is clearly defined. Therefore, in that case, for a ductile material, we can call it as yield point stress by design stress or allowable working. Because for other material, ultimate stress we can easily find out. But for ductile material, we can also find out the yield point. That permanent deformation starts from yield point only. Therefore, instead of taking ultimate stress, if we take yield point stress, then the safety will be more. Therefore, yield point stress to design stress. Therefore, if we allow that the factor of safety, we can calculate based on this. What is the significance or importance of FOS, that is factor of safety? A factor of safety increases the safety of people and reduces the risk of failure of a product. That's what I was saying. So when it comes to safety equipment and fall protection, the factor of safety is extremely important. And if a structure or machine fails, there is a risk of injury and death as well as the company, and it is also a financial loss. For example, when a company is gone for a major project or whatever the projects may be, if anything is failure, it's a loss to the company and loss to its reputation also. That's why this factor of safety is very important from the point of safety as well as protection and financial wise also. That's why we have to take the design stress or allowable stress should always be less than the ultimate or yield point stresses of a material. Now, what is a lateral strain? When a bar is subjected to a tensile load, its length increases and its lateral size decreases. Diameter or width decreases. See here. So similarly, when it is subjected to compressive load, its length decreases and its lateral size, that is diameter or width, increases. So when it is subjected to tensile stress, length increases and cross-sectional area decreases. Whether it is maybe a circular rod or a rectangular one, its diameter or width decreases. When it is compressed, its length decreases and its other dimension, that is the diameter or width, will increases. So what do you mean by lateral strain? So here we see here the first one, it is subjected to elongation, that is tensile load. When it is tensile load is applied, we see the length increases, the length is increased, and so L plus delta L it has become, and its diameter, see here, it was earlier it was D, now it is D minus delta D. This is called this is reduction, increase in the lateral dimension and decrease in the increase in the lateral dimension, decrease in the linear dimension, that is primary dimension. Here if we say compressive stress, so its length decreased and lateral one increases. So when the tensile load is there, length increases and its lateral thing decreases. For a compressive strain, compressive load, its length decreases and lateral diameter increases. This is what we have. Now, the ratio of axial deformation, that is change in length to its original length, is called longitudinal strain. That means, or linear strain or a primary strain. That means the deformation along the axis, that is called axial deformation. That means in the direction of the load applied. That means it is talking about the lengths. Here you see the dimension which is changing along the direction of the load is here length, here also length. So change in length by original length is called longitudinal strain or a linear strain or a primary strain. So, and the strain at right angles to the direction of the applied load is called lateral strain. So change in diameter by original diameter, but the diameter is perpendicular, the dimension which is perpendicular to the axis, that axial load. Therefore, the strain at right angles to the direction of applied loads is called lateral strain or secondary strain. That is change in diameter by original diameter or a change in width by original width is called lateral strain or secondary strain. So we have to clearly understand the longitudinal strain or a linear strain or a primary strain is the strain related to the axial deformation, that is change in length by original length. Change in diameter by original diameter, that is perpendicular to the axis, the axial force, then it is called lateral strain. The change in diameter by original diameter is a lateral strain. So this is what we have. For a circular bar, length L and a diameter D, then a longitudinal strain is delta L by L. And lateral strain is delta D by D. This is for circular bar. Whether it may be a compressive stress or a tensile stress or a compressive load or a tensile load, the delta L by L is a longitudinal strain and lateral strain is delta D by D. For a rectangular bar of length L and width D, if you say width D, then the longitudinal strain is delta L by L and a lateral strain is delta D by D. This is what we have. Now we will try to understand what is Poisson's ratio. The ratio of lateral strain to the longitudinal strain is called Poisson's ratio. So Poisson's ratio is nothing but it is denoted by 1 by m or mu. In most of the textbooks, it is written as 1 by m, and in some textbooks it is written as mu. Therefore, longitudinal strain by lateral strain by longitudinal strain. The ratio of lateral strain by longitudinal strain is called Poisson's ratio. So Poisson's ratio m 1 by m is equal to lateral strain by longitudinal strain. Why it is denoted with m? So earlier m is defined as a longitudinal strain by lateral strain. Then they have changed it to Poisson's ratio as 1 by m, that is lateral strain by longitudinal strain. That's why it is indicated with 1 by m or mu. Now we will go through the various relations between various elastic constants. We have seen in this video lesson only we have three elastic constants such as Young's modulus or modulus of elasticity, modulus of rigidity, and bulk modulus. How these are related to each other. So if the Young's modulus of a material is E and modulus of rigidity is C, bulk modulus is K, and Poisson's ratio is 1 by n, then the relation between Young's modulus or modulus of elasticity to modulus of rigidity is indicated with E equal to 2C into 1 plus 1 by m. That is Young's modulus equal to 2 times modulus of rigidity into 1 plus Poisson's ratio, that is 1 plus 1 by m. This is what we have. Now, the relation between E and K, that is Young's modulus or modulus of elasticity to its bulk modulus. So E is equal to 3K into 1 minus 2 by m. That is Young's modulus equal to 3 times bulk modulus into 1 minus 2 times of Poisson's ratio. So this is what we have. And the relation between E, C and K without Poisson's ratio, if at all we want to find out, so it will be E equal to 9kc by 3k plus C. This is what we have. So derivation, how we got these things are not important for diploma level. So, and also we want a relation between C and K, including M, 1 by m. So if we get these two things, we will get a relation between C, K and m, 1 by m. So you will get a relation. If you want to get a relation purely on E, C and K, E equal to 9k C by 3k plus. So these are the relation between elastic constant. So while solving the numerical problems, this formula will be helpful for us. So this is what we have. Almost we have covered entire thing of the chapter called stresses and strains. So if you have any doubts, please get back to me. Please go through my channel regularly so that you will get updates, latest topics on this also. You can go through it. So this is from my side, and if you have any doubts, you can raise, you can post your questions in the WhatsApp groups, or you can post your doubts through mail. My mail ID is padavalaanand@gmail.com, padavalaanand@gmail.com. So this is what we have. Thank you very much for watching this video. Please give me the feedback so that I can improve in due course of time. Thank you, one and all.